Mount Etna erupted suddenly as ash and fire poured from the summit, while instruments began registering far more dangerous signals. The eruption was violent and without any gradual buildup scientists normally expect, sending dense ash columns and incandescent material into the sky. Monitoring stations recorded rapid pressure release, while seismic sensors detected deep tremors migrating laterally instead of vertically. That detail immediately raised concern. Additional analysis showed that the tremor pathways followed older fracture zones rather than central conduits, suggesting stress was being redirected into pre-weakened areas of the volcano. Infrasound arrays also detected irregular pressure pulses inconsistent with normal magma ascent, indicating unstable internal dynamics. Gas ratios measured at summit vents showed sudden spikes in sulfur dioxide relative to carbon dioxide, a signal often associated with rapid decompression at depth. Together, these indicators suggested the eruption was interacting with deeper structural weaknesses rather than simply venting surface pressure. This behavior broke from Etna's normal eruptive pattern. Lava output was uneven, vents opened asymmetrically, and energy was being released toward the volcano's seaward side. Thermal imaging showed abnormal heat spreading across the southeastern flank within minutes. Civil aviation alerts were issued as ash drifted unpredictably, but researchers were focused elsewhere. Ground deformation sensors began registering sudden microshifts along the slope facing the Ionian Sea. These movements were small, but unusually fast. Past data showed Etna's greatest hazards often emerged during eruptions, but not from lava alone. As data streamed in, scientists realized the eruption may have destabilized whole parts of the mountain already under long-term strain. The eruption itself was dramatic, but it was likely only the trigger. What scientists noticed next shifted concern from eruption toward something far worse. Attention quickly shifted to Mount Etna's southeastern flank, a massive section of the volcano already known to creep slowly toward the Ionian Sea. New GPS and laser measurements showed that this movement had accelerated sharply during the eruption. What once slid millimeters per year was now shifting centimeters in days. Tilt meters installed along the flank recorded subtle rotational movement, implying the mass was not just sliding, but beginning to pivot outward. Marine sonar surveys offshore also detected fresh sediment disturbances aligned with the slope above, suggesting early underwater displacement. Researchers noted that rainfall, seismic shaking, and eruptive vibrations can temporarily remove friction along clay-rich layers buried within the flank. Once those layers weaken, movement can accelerate rapidly without additional warning. Seismic data confirmed shallow tremors clustering directly beneath the slope, suggesting internal weakening rather than surface erosion. Scientists noted that the eruption's energy release appeared to reduce friction along buried faults, allowing gravity to take over. Historical records showed that this flank had failed before on smaller scales, often during eruptive periods. The concern was no longer theoretical. The mountain was moving, and it was moving seaward. And as the flank shifted, instruments detected something forcing the mountain outward from within. Beneath the unstable flank, sensors detected fresh magma intrusions spreading laterally instead of rising straight upward. This magma was forcing its way into existing cracks and mechanically weak zones throughout the volcano's interior and structure. Pressure readings spiked rapidly, while gas emissions increased along the lower slopes. Geochemical sampling revealed elevated helium-3 concentrations, a tracer linked directly to deep mantle sources rather than shallow magma pockets. This confirmed that the intrusions were being fed from deeper reservoirs, increasing the volume and force involved. Borehole strain meters also detected expansion at depths previously considered stable. Scientists warned that this type of intrusion can bypass traditional pressure release pathways, allowing stress to accumulate laterally instead of dissipating through eruption alone. Experts warned that this outward push reduced the mountain's internal cohesion, making large sections behave less like solid rock and more like a fractured mass. Unlike typical eruptions, this magma was destabilizing the volcano's foundation rather than relieving pressure. Each intrusion widened fractures, increasing the risk of sudden structural failure. Etna was no longer just releasing pressure, it was losing structural integrity. That internal pressure soon became visible where the volcano met the coastline.
The terrifying rumbling sound of explosions sent this tour group scrambling. This is called touching the impossible, this Mount Etna tour guide says.
Satellite radar imagery revealed dramatic ground deformation along Etna's coastal-facing slopes. Entire sections of terrain showed measurable movement between daily passes, something rarely observed outside major collapses. In some areas, the ground bulged upward, while adjacent zones sank, indicating uneven stress redistribution. Interferometric radar comparisons showed deformation boundaries aligning with known fault scarps, effectively mapping where separation was actively occurring. Engineers monitoring nearby infrastructure reported microfracturing in buried pipelines and retaining walls, confirming deformation was not confined to uninhabited slopes. Ocean bottom pressure sensors detected slight but sudden changes in water column height near the coast, reinforcing concerns that land movement was already transferring energy into the marine environment. These signals confirmed that deformation was already coupling land movement directly to the marine system. The speed of deformation exceeded anything typically seen outside major collapses. Models suggested that continued movement could allow large volumes of rock to detach suddenly. The data confirmed a critical reality. Etna's instability was no longer slow or predictable. The volcano was changing shape in real time. If that motion continued, the sea below could be violently affected next. Geologists began comparing real-time data with evidence from Etna's ancient flank collapses and similar events worldwide. Geological layers offshore revealed massive debris fields, proof that entire sections of the volcano had collapsed into the sea thousands of years ago. In those cases, eruptions were not the main destructive force. Damage scales were determined by collapse volume and speed, not eruption size. Studies showed that these failures often followed periods of accelerated ground movement, magma intrusion, and coastal deformation, patterns now reappearing. Comparative studies from volcanoes such as Anak Krakatau and Ritter Island showed similar precursor sequences before catastrophic flank collapse. In those cases, satellite data later revealed acceleration phases that lasted only days to weeks before failure. Researchers emphasized that once a flank enters this stage, historical timelines compress dramatically. The lack of prolonged warning periods makes reliance on visual eruption intensely misleading when assessing true collapse risk. Experts stressed that collapses happened abruptly, without dramatic eruptive finales. Etna's past made one point clear: the greatest danger came when the mountain gave way, not when it erupted. Those ancient lessons pointed toward a threat forming where rock met water below. Scientists emphasized that the Ionian Sea transformed a geological collapse into a regional hazard. If part of Etna's flank slid underwater, it would displace enormous volumes of water almost instantly. The displacement would occur faster than any warning system could meaningfully respond. The force would radiate outward from the collapse zone, amplifying as it traveled. Bathymetric mapping showed that the seafloor of Etna drops off steeply, a geometry that favors rapid wave formation rather than gradual dispersion. Scientists explained that underwater landslides convert gravitational energy directly into vertical water displacement, making them far more efficient tsunami generators than earthquakes of similar size. The shallow continental shelf near Sicily would further compress incoming waves, increasing coastal run-up heights within minutes. Even a partial slide could generate waves far larger than historical Mediterranean tsunamis. Researchers warned that coastal defenses offered little protection against such a sudden energy transfer. The sea, not the lava, represented the fastest and most dangerous pathway for destruction. That realization pushed scientists to model what those waves might actually look like. Advanced simulations were rushed into action using updated deformation and volume estimates. The results altered risk assessments immediately. Models showed that a collapsing flank could generate towering waves racing towards Sicily's eastern coast within minutes. Some scenarios indicated wave heights exceeding anything recorded in the region's modern history. Worst-case simulations showed wave fronts crossing open water so rapidly that detection and alert would occur nearly simultaneously. Reflections from basin walls created complex interference patterns, causing unpredictable amplification at certain coastlines. Emergency planners noted that traditional tsunami thresholds used for earthquake alerts failed to capture this type of sudden landscape-driven surge. This forced scientists to revise assumptions about Mediterranean tsunami ceilings upward. Narrow bays and harbors amplified the surge, funneling energy directly inland. Warning systems would have almost no time to respond. In many projections, evacuation windows were measured in minutes, not hours. The simulations removed any remaining doubt. This was not a distant or theoretical risk, but the danger did not stop with Sicily's coastline in those projections. Researchers warned that the Mediterranean's enclosed shape could carry tsunami energy far beyond the initial impact zone. After striking Sicily, secondary waves were shown to radiate across the basin. Southern Italy faced rapid rebound surges, while Malta and parts of Greece could experience delayed but powerful flooding. North African coastlines were also included in worst-case scenarios, particularly in low-lying ports. Harbor resonance modeling revealed that even moderate incoming waves could oscillate repeatedly within enclosed ports, extending flooding duration long after initial impact. Researchers also warned of secondary hazards, including fuel tank displacement, ship collisions, and infrastructure failure caused by rapid water withdrawal after surge arrival. Because warning times varied by location, some regions could be struck during tidal peaks, compounding flood severity beyond modeled averages. Although smaller than the initial wave, arrival timing varied sharply between coastlines. The models showed the effects would not remain localized. Etna's instability had quietly become a Mediterranean-wide concern. With so many regions exposed, attention turned back to the mountain's next move. Civilian protection agencies evaluated evacuation plans under rapidly changing conditions. Modeling showed that coastal communities closest to Etna's southeastern flank would have extremely limited time to react. Narrow roads, dense populations, and nighttime scenarios complicated every projection. Officials acknowledged that sirens and alerts might reach residents only minutes before impact. Mobile alert systems were further limited by network congestion during seismic events, reducing message delivery reliability. In rural coastal zones, some communities lacked real-time warning infrastructure altogether. Emergency managers also noted that tsunami evacuation routes often overlapped with landslide-prone roads, potentially becoming impassable during flank movement. These constraints forced planners to assume partial exposure rather than full evacuation in several zones. But some areas simply could not evacuate fast enough, no matter the preparation. Authorities focused on risk reduction rather than full relocation, a sobering shift in strategy. The eruption exposed a hard truth. Modern systems still struggled against sudden geological collapse. That reality forced scientists to confront why this moment felt fundamentally different. Researchers emphasized that no single signal caused the alarm. It was the convergence. The eruption had already destabilized the system. The southeastern flank was accelerating, magma pressure was pushing outward, and the sea sat directly in the collapse path. Each factor amplified the others. Risk analysts explained that compound hazards dramatically increase failure probability even when individual indicators remain below extreme thresholds. Small seismic shifts could trigger larger responses once structural limits are crossed. Researchers compared the system to a compressed spring, where stored energy matters more than visible motion. This non-linear behavior meant traditional forecasting windows were shrinking faster than expected, leaving little margin for corrective intervention. Scientists also stressed this was not speculation or panic-driven messaging. Probability windows were narrowing based on measurable trends, not worst-case imagination. The concern was timing, not certainty. Etna has entered a nonlinear phase where minor inputs could trigger system-wide failure. That instability, experts warned, was the most dangerous phase of all. At this point, control is no longer part of the equation. Let us know your thoughts in the comments.